that people leave questions either over there or on this Zoom chat, but I don't see a lot of participants already in the Zoom chat, so I'll have to check at both places. All right, well, so let's get started with this talk. It's our pleasure to have Aditya Sharath from GitHub talking to us on his work on CodeQL. I should also mention that in the previous version of the program, Ogada Moore was going to give this talk, but he had some personal business to attend to. And so Aditya kindly agreed to talk, to speak to us on the work that he does for CodeQL. And Aditya has been with GitHub for a little while, and then with Semmle for a while. And before that, he did his master's and bachelor's from Oxford. So Aditya, over to you. We look forward to your talk.
Wonderful. Thank you, Satish. Very happy to be here. As Satish mentioned, I've worked with Semmle and GitHub for a number of years now. And the technology that I'm talking about today is called CodeQL. This is what came out of the startup company known as Semmle and is now part of GitHub. And we are very excited about the ability that this technology has to provide code analysis and security coverage. And I'll talk you through some of the details and why this was valuable for a smaller company and continues to be valuable today. The focus here is an idea called variant analysis. So first, let's see what that means. I'm going to take you back a little bit to 2012 and the time when the Curiosity Mars mission was underway. During this time, with Curiosity in flight, NASA's JPL discovered a mission-critical bug in one of its modules, specifically the landing module, which is software written in C that integrates with the landing hardware. And they discovered this bug in the software through manual inspection of the code itself. A simplified version of the code, I don't have the real thing, but it looks something like this. There was a function that handles the firing of the thrusters in the landing module, and it accepts an array of vectors with coordinates for different aspects of the module. And one might call this function in order to fire those thrusters by providing it information about the coordinates of each part of the module. So what's wrong with this code? Well, we see that the numbers don't match up. It's expecting something of length 12. In practice, it was given something of length 3. And a quirk of the C language in this case is that this annotation that tells you the size of the array in the parameter is erased at compile time. It is not something that is checked, where you would normally expect an error when these two things don't match up. In this case, the 12 is ignored in this declaration of vectors. The value that was provided to this function as the actual argument was shorter than expected. And so we get an out of bounds read when we try to read 12 elements out of an array of length 3, which could lead to reading off the wrong part of the stack, undefined behavior. Generally terrible if you are in a situation where you are writing mission critical software which has very strict constraints that it must follow to interact with the hardware. And an important consideration here is I might be able to fix this problem. Have I got it lurking anywhere else in my code base? So at the time, JPL talked to the company then known as Semmle, and they used their code analysis technology called QL to write a query to describe this pattern. The query looked something like this. We won't go into the syntax in detail now, but I will show you in some detail later. We look for functions, calls to those functions, and we try and compute the expected and actual sizes of those array parameters that we saw on the previous slide. Without knowing the details of this language, hopefully you can still read this kind of from left to right and see the meaning that it is trying to convey. We look for two sizes. One is the one that is expected in the parameter. One is the one in the argument that was actually passed. And we complain when the actual size is less than the expected size. This is like an SQL query in the sense that you have a from where select. You choose some output to report as your result. Now JPL ran this query. They found the original problem, but many others, a total of 30. And to their great credit, they were able to fix this remotely while Curiosity was in flight. And we know the happy ending of the story. It landed successfully, and this mission continues to go well. Now I will fast forward to the present year. A different setting, a different kind of security or correctness issue. In this case, the research group called GitHub Security Lab, some of my esteemed colleagues, reported a remote code execution vulnerability in an open source container orchestration platform. This is Java code. It's the basis of part of Netflix, in fact. And the code looks something like this. Again, this is simplified. But there was some validation of an input object that might be untrusted. And when validation fails, an error message is produced. That's what this build constraint violation with template method is doing. This is dangerous if this untrusted data that's being validated ends up in the error message. So we see here that common is a set constructed from some information from the untrusted data. Why? Because when building this template message, it is possible that Java expression language code that is in the input will get executed. So if your input is untrusted, your input contains code statements in this expression language, they will get executed in the template. That's dangerous because an attacker or someone submitting data to your platform has control over code that's getting executed on the backend. So they identified this vulnerability and they looked for this particular pattern. And in the same QL, now called CodeQL, query language, looked for this across open source Java projects on the GitHub ecosystem. And this led to a number of interesting results, all of which were responsibly disclosed and fixed. And a demonstration of the impact of this kind of vulnerability or the need to find these kind of things is one of the projects was Germany's COVID-19 contact tracing infrastructure, which is highly relevant in the present year. And this is not handling personalized data. It's anonymous information that comes from the contact tracing app and sends notices of positive infection tests up to the server. And the vulnerability here was in the server. As it was processing those anonymous notifications, it could have had code execution if there was code embedded in the right way inside the payload. A simplified version of the code looks something like this. We have another of these isValid functions that's doing some validation. It's accepting a payload. It does a number of checks, many of which I've omitted here, but one of the things that it checked was that the payload is coming from an origin country that the server recognizes or has data for. If we look at what that function does, it will, as you might expect, look up the country from the payload, and it will add a violation message if the country is not part of a given list. And when adding a violation message, we see our old friend, build constraint violation with template, which, as I explained previously, is going to execute code if untrusted code is passed to it. There's a great blog post on the Security Lab website about this, which is available at this link. What do these patterns have in common? They tell us that we found an initial vulnerability. We figured out a way to fix it. We identified a pattern that was important. But that vulnerability happened again, sometimes in the same code base, sometimes in a different code base. The moral here is that software vulnerabilities, whether we're thinking about security or thinking about correctness, I think they're both severe and they're both vulnerabilities. They rarely occur in isolation. And the process of discovering other vulnerabilities that follow the pattern of one that you've already found is what we call variant analysis. And this is a term used by experienced security teams at leading technology companies, among other places, as they do this process of discovery. Whenever they discover a seed vulnerability, it is important that they understand why it happened and also explore to see whether there are other vulnerabilities of the same nature. However, this is pretty hard. It's often a very manual process to be combing through the code to understand how this pattern might occur. If your pattern is very simple, you can kind of eyeball the code, you can use grep, textual matching is generally fine. But if you look at the three-step process we had before for the Corona Warn app server, that's not the kind of thing you want to be staring at the code, trying to poke through. It's not a good use of a security team's time either. But it does require this combination of effort and expertise in order to correctly identify these problems. Now, this tells me, as someone who's making developer tooling and working on programming languages, that there's room for automation. And it's important here to think about what a good tool for variant analysis looks like. If we want to give the software engineering and cybersecurity industry the right tools for this, it had better solve the problems that they care about. I argue that there's many considerations here, but I argue that there's a handful that are particularly crucial if you want such a tool to be used and adopted. Efficiency is pretty important. There was a really good talk earlier in this track series by Dr. Kristen Yvonne Rosier about, interestingly enough, things to do with NASA and securing flight software. And she spoke about efficiency, or the ability to scale up to real-world code bases, and the need for tools to actually be able to solve problems on the real code that is potentially vulnerable. You've got to be able to handle real applications at potentially open source enterprise scale. Similarly, it must be expressive. You must be able to say the things, describe the patterns that you care about in the code. A kind of fixed set of rules that you look for, or a one-size-fits-all approach, is not particularly effective. A lack of expressivity also leads to noise, and this has contributed a little bit to some industry distrust with conventional static analysis tools, where they might produce a lot of results, some of which will be things that you should really be fixing, but they're often hidden among a lot of noise. And an expressive tool allows you to customize what it's doing. It allows you to take away false positives and make things more precise. And finally, we're not trying to replace human expertise. We're not trying to replace even the tools that led to the original discovery of the vulnerability. Variant analysis is about expanding your reach, multiplying your force, encoding expert knowledge that software engineering and computer science and security experts have in a form that can be shared and reused. So you've discovered a vulnerability. You want to make sure that other people know about this vulnerability that you've discovered, and they can use that knowledge from you in a way that is repeatable and executable and automatable. So keep these things in mind: efficiency, expressivity, and the ability to encode expert knowledge. Speaking to this audience, we think about programming languages and programming tools. This kind of sounds like you're writing a program, right? You're encoding knowledge about execution, some instructions to the computer. You want it to be executed quickly. You want to be able to say and do the things that you need. So we can think about this from the lens of writing programs to solve these problems for us. And that brings us to the technology that we work on, which is called CodeQL. It is a code analysis engine. It is a semantic code analysis engine, so it is able to reason about both the structure and the meaning of the source code. It does so statically at compiler build time. And its purpose is to find errors and vulnerabilities in source code. It's capable of handling a pretty wide range of languages, in principle any language, as long as you can provide the right mechanism of extracting the code written in that language into the form of relational data, which is what CodeQL processes. And in order to operate on this data, it has a declarative logic programming language, which allows you to describe the patterns that you want to find, a bit like the examples we saw previously. Importantly, this is an object-oriented query language. This is a little bit unusual, but it allows us to create reusable libraries, reusable structures that let you describe patterns in a convenient way. And finally, what happens under the hood? What are we actually doing with them? This is really building on a whole lot of research that may also be familiar to some of this audience about both extracting source code, operating on relational databases, and representing source code in that relational form, and using data log queries as an efficiently executable way of obtaining information from such a database and processing it. So CodeQL query becomes optimized data log, which we evaluate to find code analysis results. I'll take you through a little bit more of the detail of the kind of high-level processes that I described on the previous slide. Think of a database scheme that describes code in the form of relational data. It might have a number of tables for different patterns that we care about. There will be a different scheme for each language. So you might imagine that for Java, there's a table of expressions, a table of statements, a table of methods, and you might have links between them through standard index and key mechanisms. And now you've got a code base. If you want to extract this code base into the form of data, a reliable way to get information from it is by looking at the source code and looking at the build system. Conventionally, a build system will process the source code. For a compiled language, it will run the compiler, and it will produce some artifacts of your software. We don't care about those final artifacts, but from the point of view of CodeQL and static analysis, we extract the code during the build. For a compiled language, this is something like piggybacking on the compiler, seeing all the source code files that it touches, the information that the compiler produces. And so you see this arrow from the build system going to the extractor. For an interpreted language, something like JavaScript or Python, there's no compilation or build, so to speak. So it's enough to scan all the source files and run your own parsing in order to get information out of them. Regardless of those two paths, we've obtained information from the source code, and now we use it to populate the database scheme. The data from the source code gets populated in these tables, and now you have a database. This is just something on your file system which contains a lot of data about a software project at a particular point of time. Now I have a database. It represents information about my source code, syntactic information, structural information, maybe locations. What do I do with it? I want to get some information back out. So I need to query it. One could write a CodeQL query in the declarative query language that I described, combined with libraries. It's important here for things to be reusable. I don't want you as a writer of such a query to have to write every time what it means for a method to be in Java, or what it means for a method to belong to a particular type, or sometimes even to describe common security patterns. It's useful to have reusable libraries that model key concepts within the language that you're targeting. And for us, these are open source. We have open source repositories with all the standard queries and standard libraries, which find well-known problems in code and can be built upon to find custom problems in code. So these queries get compiled against the database scheme. Compilation takes your query written in our kind of custom language into Datalog, and then is heavily optimized. So there's a lot of standing on the shoulders of giants here, a lot of building on research into Datalog optimization, logical transformations, program analysis, and that Datalog gets turned into database relational algebra expressions, which are also optimized a little bit more. Those are run through an evaluation engine that we also maintain against the database. So now we are processing relational data in the form of tuples to execute a Datalog program or a relational algebra program. And this produces results which correspond to the bugs in your code, the patterns that you want to find, the errors and vulnerabilities that you are interested in. Now, you've seen some examples previously about what a query looks like, particularly for the first example. And you've seen the kind of high-level process of how these queries get processed. What does a query look like? It's a little bit like SQL, from where select, maybe in the wrong order if you're used to that. The from declares some variables and their types, saying that these must come from these sets of values. In this case, a method access is a call to a method in Java. An expression is a program expression that might have a value. We declare some restrictions on those variables through the where clause. In this case, we are looking for a method whose name is build constraint violation with template. And the argument is the first argument, index 0, of this particular method. Finally, we have a select clause that decides the output. In this case, we choose a code element, the expression argument, and we choose a string to provide a message to the user. Overall, this query clause describes what pattern we are trying to find, and it relies on imports. It relies on this method access type, this expression type, these built-in things that look like functions but are not quite, get method and has name. All these are coming from the standard libraries that we've written for Java, for CodeQL analysis of Java. And so these imports let you reuse logic in other modules. So we've gone through kind of the motivation for why it is important to have technology capable of variant analysis and some examples of what that looks like in the wild. I've shown you the process of CodeQL compilation and processing, not the details, but a high-level overview of how you go from source code to getting some results out of it. And you've seen a little bit of the query language. And what I'd like to take you through very quickly is a more detailed dive into the second example, the Java bean validation example. We won't look at the Corona app server. We'll look at the original vulnerability in the container orchestration platform. I hope that you can now see my editor window. Great. So this is the CodeQL extension for Visual Studio Code. This is the main development environment for a CodeQL query. And I've got a CodeQL database of the project I mentioned. It's called Titus control plane. And this has gone through that extraction process that takes the source code and puts it into the form of data. And now I've got the boilerplate of a CodeQL query. We don't need to familiarize ourselves with all the elements here. Some of this is just metadata. But you see that there is a from-where select at the end. And I'm interested in finding a particular pattern within this code. You remember the example that we saw. We look for these validation methods and the inputs to those. Those are considered untrusted. And we look for, within those validation methods of the data that they might pass on, places that might build an error message with a template that might execute that code. So we're going to convert that knowledge of the code pattern into knowledge of a description in CodeQL that encodes it. I have a kind of template here for what's called a taint tracking configuration. CodeQL is capable of pretty sophisticated interprocedural data flow analysis, and this configuration is boilerplate that lets us access that. So we describe two endpoints in the data flow graph of the program where information might flow, and it will look for paths between them. And in security terms, this is a vulnerability. If you can go from a place where untrusted data enters your program to a place where you do something dangerous with it, that flow leads to a vulnerability. So I'm going to focus on these things that look like functions. They're predicates, they are relations, they might be multi-valued, the building block of a CodeQL query. And I'm going to describe what it means to be a source or a sink for this vulnerability, something untrusted or something dangerous. Let's start with the endpoint. I think that's easier to describe. I remember saying that the method was called build constraint validation with template. So I'll write that down to remind myself. And what do I care about here? I must say something about this sink. So I will say that it is an expression. I will say that there is a method access, a call to a method. I'll call it MA. What do I know about this method access? I know that this method access calls a certain method, and that method has a name. I hope it has a name, which is what I wrote out here. And I care about a particular argument of a call to that method. I'll say that the sink is an argument of such a method call. I could be more precise and put in an index number and say it's this particular argument. In this case, it doesn't really matter. So I will evaluate just this piece of logic to make sure I'm on the right track. This is called quick evaluation. This calls me different. It's because I named it wrong. It's build constraint violation with template. Let's try that one again. That's more like it. This is why it's helpful to debug your predicates as you write them. Otherwise, you end up with no results and are surprised. So if we look at some of the results here in the code base, we see this pattern that I described to you. I see that there is a call to such a function, and I see that there are arguments to that call. And this is the thing that gets executed. So far, seems like I'm on the right track. So this is one end of the problem. If something reaches this point in the code, I have a vulnerability. Okay, now what are the kind of unsafe things I don't want to reach at this point in the code? Well, the pattern I showed you previously was the first parameter of something called isValid. So I can do something similar here and simple. I can say that there is a method, it's called m, and I can say that m has the name isValid, and the source is the parameter of that method. It's the first parameter of that method. So let's evaluate that and see what we get. Okay, there's a bunch of these parameters. And that seems reasonable. I could be more precise, in fact, and say that it is a method on this particular type, and that's implemented. So maybe I will do that just to be a little bit more precise. So there is an implementation of the method, call it impl, and we say that it overrides the original isValid method on the upper validator interface. I can do things like transitive closure in CodeQL, so I can say that it might override or instantiate through 0 or more steps. And the source is actually the parameter of the implementation. Maybe I want to add a restriction saying that this is to do with types. I want to say that it's only on this particular validation type that I care about. So I could say the declaring type of the implementation method has the name. Let's have a look at what this one was here. Constraint validate. Java x.validation.constraint validate. In fact, I can go all the way and write the fully qualified name. Just taking us a bit from just a simple textual match to something that really uses the type information that we have from the compiler. Again, to be sure I've written this correctly, I'm going to evaluate it. And this, because the implementations type is not that, it is the original methods type. So let's do that one again. That's more like it. So now we've narrowed down our results a little bit. We're only looking at the ones that are really validators that are going to process untrusted data. And they all have a first argument, which we consider untrusted. So to rephrase what we wrote in CodeQL, we're looking for methods that look like this. They're called isValid. They override the isValid declaration in constraint validator, which is an interface. Now I've got these two building blocks put together. I've got the two endpoints of the problem that I care about. Let me join them up. So we see that the from where select part of this query has something called has flow path. It says that there is information flow from one to the other. Now, if I run the entire query rather than just the pieces, it will tell me whether any of these sources that I described can be wired up to the sinks that I described, which tells me that there's a vulnerability. And when I do so, I see that I get an alert at a particular location. I can find the source that was this container object that's being validated. And I can see that it goes into common, and common's data is used here. And this is the example that I showed you on the slide. And we could extend this query, keep investigating what kinds of results we found, run it on other projects and see what the results are. And as a quick demonstration of what the capabilities of this are like, if you fully expand them to their fullest potential, here is a more sophisticated version of this query that actually tracks all different kinds of remote user input that appear in the application and is capable of tracking through, in this case, Hibernate's expression validation capabilities. So we won't go into the details of how this works here, although I'm very happy to share this with you. But what it does show you is CodeQL's capabilities of doing interprocedural data flow analysis through quite a long sequence of steps. So we can start with something like the endpoint that handles an HTTP post request that takes some data from the user. We can see how that data is used and trace it through the program. We can see getting values out of that. We'll click on every single step here, but eventually if we go further on, we see the place where this is being validated. This is our friend, the isValid method, and a place where this constraint violation is built. So we've traced all the way from untrusted input in a totally different part of the program down to a dangerous execution that might execute Java code. The slides here, which I'm happy to share later, have a description of the patterns that we found. You've seen it live, so I don't need to take you through that again. But this will hopefully give you an idea of how to map between code in a target programming language and code in CodeQL. Something I didn't go into a lot of detail is that CodeQL is heavily customizable in this case. So we've actually added some extra team steps, extra data flow analysis steps that the library did not know out of the box, but it's very easy to add them if necessary when you are looking for these security vulnerabilities. And the final query, as we saw, looks something like this, where we describe a source, a sink, maybe some extra steps, and we look for a path between sources and sinks. So hopefully now you're convinced that variant analysis is a thing that we have to be doing. It is valuable to the industry, and are at least somewhat convinced of the capabilities of the CodeQL tool for tackling this kind of problem. Now, what makes it really feasible for this? Why is this effective? Why was this small company that created this technology able to provide value in this sense? Going back to the principles that I described earlier, we want such a tool to be efficient, and by bringing together the best of academic research and industrial practice in compilers and databases, in Datalog, we made CodeQL efficient. It scales up to millions of lines of code. We can process billions of tuples. You don't want to be doing that all the time. It's heavily optimized to try and get the best performance and the right order of evaluation in the queries that you write. But it's capable of handling these large-scale code bases. It's expressive. You've seen in a few minutes how we can write a pretty reasonable security query that finds genuine vulnerabilities. You've seen a little bit of its capabilities for interprocedural data flow analysis, which is really important if you're trying to find security vulnerabilities. And it's highly customizable. So this also makes it quite easy to get rid of false positives. You modify the query that you've written based on your knowledge of what makes a true or false positive result. And this is done by bringing together a lot of knowledge and expertise in program analysis. We're not trying to reinvent everything here. We are providing a platform, a general purpose tool that is able to express different forms of analysis. Finally, you can't really do this on your own. Otherwise, it would be very much limited to the number of people who work on CodeQL technology who knew how to find certain kinds of vulnerabilities or look for these patterns. So a lot of our effort has been focused on creating a community of contributors where the queries and libraries are open source. We encourage developers and security researchers to contribute to it. And this means that those queries that you see are encoding a wide community's expert knowledge of program analysis and security that is continually growing. And the relevance here for us, at the time, small company like Semmle, and then even now as it's a trusted industry tool and part of a larger platform like GitHub, was that variant analysis is valuable. This was solving a unique problem that many security teams had to handle manually, while being distinct from traditional static analysis capabilities, in the sense that you're not just scanning a code base, producing some results, and hoping that people will look at it, but there is expressivity and customizability involved. You can make it more precise, you can deliver meaningful results that hopefully people are going to take seriously and fix. And so far, this has been working pretty well, and we're really proud of what we've been able to create and share. It's important that we keep making this work. So the journey doesn't stop here. We're not sitting on our laurels. We continue to apply ideas in my team from computer science research and our own experience, both to improve the program analysis capabilities of the queries that are written, as well as the scalability of the engine and how it performs as it scans real-world code bases. It's also important to solve the problems that are relevant to the software engineering community. So different languages and frameworks that they're actually using, maybe new ways that we can recognize security relevant patterns in code without necessarily having to manually encode all of that knowledge. We're exploring different areas in this direction. And it's useful to give developers and security teams results that they're going to care about and results that they're going to fix, ideally in a way that explains the problem very well. So you've seen the kind of path visualization that I showed you in the editor. GitHub code scanning also runs this analysis at scale as part of continuous integration testing. And that's now, as of this year, freely available for open source projects. So having this technology and also providing a way for people to use it in real world software is really important. Finally, variant analysis is done best with other people. It's a community. We encourage contributions. We try and learn from those. I've spoken about GitHub Security Lab, who are a research division who work very closely with the CodeQL core technology and find lots of valuable and interesting things like the examples you've seen in this presentation. So we are trying to do this together and make sure that the tools are capable of bringing people, bringing computer scientists, software engineers, security researchers together to find ways to create better software. With that, I think we're up to time. I'm very happy to answer questions, go into a little bit more of the details of what we do and how these processes work, or generally hear what you think about these ideas.
Thank you, Aditya, for that wonderful talk. I will wait for questions to appear either on the Clouder platform or on Zoom. At this very moment, I do not see any questions. But while we see if people do have questions, maybe I can start off. So this is all wonderful stuff. I wonder, would you be willing to get into a little bit of how Semmle or CodeQL accomplish this level of efficiency, which has been generally a pretty elusive goal as far as carrying out any kind of program analysis on very large code bases is concerned. Even creating any kind of high quality call graph may be fairly challenging, especially for languages such as JavaScript and so forth. So whatever you can share about what's the secret sauce here, what kind of techniques did you use for achieving that level of efficiency?
Sure, that's a great question. It's true that scaling to those, reaching that scale is difficult. And sometimes applying the ideas that you kind of come up from the original research and trying to make them work on large scale leads you to really unexpected challenges. I can share a little bit about the different approaches we've taken towards this. A lot of the, so there's two aspects to this, how you make things perform. I think one aspect is the engine itself. How do you make a data log query optimized, and how do you evaluate it efficiently to get to process those tuples? And then there is the analysis. How do you express your analysis in such a way that you're building up more information that you need, trying to produce a call graph or a control flow graph that is overly large or overly complex. So there's two aspects to those things. And the team that I work on focuses more on the former within the CodeQL realm. We maintain the engine, and they're pulling a lot of data log research and trying it out and seeing what sticks. There's a lot of well-known techniques, things like magic sets, things like contextual optimization. In practice, automatic join ordering. So you're taking what the user has written as a query, but figuring out the best way to evaluate it as a series of database joins. We throw almost all of these tricks at the query that you write, but have a lot of our own heuristics that we've devised over the years to make these things scale. Well, some of those are kind of proprietary and embedded in the engine, but that's the general principle. Let's take the research, performance test, and develop some intuition about what decisions are the correct ones to make. Some of these are available. We have some published papers on type inference and datalog. In fact, the compilation from QL to datalog is in a number of interesting academic papers. You can find it on the above link. And so that will give you an insight into what we do in this transformation. For
Okay.
the program analysis side, again, expertise in knowing what to create, sometimes also applying heuristics to decide what do you care about. You don't necessarily need to, you can't compute the full control flow graph. That's impossible. That's the whole thing problem. But you can choose things like we will build up local graphs and stitch them together where relevant into global graphs. The language analysis teams have all sorts of tricks for building up these ideas efficiently. And that is not secret. That stuff is open source. So if you look at the query libraries, you'll see the different heuristics that go into things like data flow analysis.
Mm-hmm. Okay, thank you. So on that former part, assuming this technology is for use by people who are outside your immediate team, if you are if you are a client of this kind of technology, how do you educate them as to cost of a pattern? Because you could imagine writing data log queries where the user writes that query and then waits for 10
A long
minutes
time.
and then 1 hour and then 2 hour and nothing is happening. And a lot of work is happening, but no output is coming and they are not quite happy. And this may be a part of just user education, because you need a kind of a mental model to be able to envision what would be a reasonable query and what would be an unreasonable query. So how do you
Yeah,
go about selling or educating your potential customers about this kind of issue?
that's also a great question. You're right. Like we can, when we're developing those queries or we're developing the standard set, then we can performance validate and make sure that whatever we've produced is going to perform well. But as soon as we're opening this up as a programming language where anyone can write code in the language, there is education involved. We do this in various ways. There's a lot of material now that's growing that is kind of tutorials based on CodeQL. So a lot of these security use cases get turned into challenges or tutorials that explain how to write it. And this helps people build intuition for how to look for patterns and where they get stuck. We do workshops as well. In fact, I've got another one coming up later this year at GitHub Universe, where, again, public audiences come in and learn about how to write queries for these patterns, a few of the tips and tricks and pitfalls when you're writing such a query, what performance looks like. Sometimes we try very hard to make people not have to think about these things when they're writing those queries. So there's a bit of responsibility on our side as developers of the tool to make it try and handle most cases well. And so unless you've completely not written the logic that you intended, the hope is that it will optimize it into a way that is executable. In practice, that's not always possible. There's always going to be occasional cases of a bad join order or a slightly inefficient evaluation, but we try hard to prevent those cases. So there's a mix. Education, when we're working with customers, there's GitHub teams who are working directly with them to share that expertise. When we're working with the open source community, we do our best to answer questions and share that knowledge too.
Okay. Let's see, is anyone saying? All right. All right. Then, well, let me then continue. So one of the things that you said was with respect to the tool being customizable, in the sense that, well, you as the user knows your business, and so maybe you can help filter out false positives. But from the kind of primitives that I saw, there is a fair bit of um, scope for false positives built into the language primitives itself. For example, when you say has CFG path, or is reachable or something like that, well, static CFGs are at best an approximation of what could happen. So a lot of times you might be warning about security vulnerabilities that actually will not happen, because the control flow in reality
Yeah,
will not happen. So in your experience, and this has been kind of the bane of lots of previous technology of this kind, that and you yourself mentioned that at the beginning of your talk, that if the tool produces too many false positives, then it becomes useless, because no one can get
we
useful
trust it.
signal out of it. At the same time, if you miss the one $1 million bug, then also it's not great. So what's CodeQL team's stance on making the right trade-off between being sound and not being too noisy?
False positives and false negatives is a hard trade-off, but one that you have to make. We are generally conservative. So this means that we try and optimize for not producing false positives. So the things, especially in the fundamental layers, so things that the control flow graph produces, things that the data flow graph produce, should be valid as much as possible, is the general approach that we take. For when you build on that to do a security analysis, it says only if I know that this is a recognized source and I know that this is a recognized thing and I can find a path between them, only then will I show you what's happening. So I guess it under approximates if you're looking at it in that way, and it's conservative in that you might not get many results, but what you get, we think, we tends to have reasonably high fidelity or likelihood that you should take a look at it. This is a trade-off. It does mean that, especially as you're setting up this kind of scanning without doing a lot of customization, there's a risk that you don't find a lot. And that's a different kind of trust question, right? People want to know that you're genuinely looking at their code and finding things that are present. So again, it's not one that we solve perfectly because there's no perfect answer, but I would say that the libraries and the design are fundamentally mostly conservative, and we try and expand the coverage of language patterns and frameworks and possible sources and sinks to prevent false negatives. So we're covering lots of possible code, but the analysis is fairly precise.
Okay.
There's a room for heuristics, I think, as well, where you might be able to write. I think for inclusion in the standard set of queries that we ship, there's a pretty high bar for precision. But if you're doing like an exploratory analysis, there's a lot of room for writing a significantly noisier set of flow steps, a set of sources and sinks, for example. And so that's another way to get around this. If, as you're in this exploratory security research phase, you can write pretty noisy steps. In fact, one of the ones that I had here for the Java query has a full through all getters, which is not usually a thing that you want in practice because the information might change, but it's pretty good if you're trying to work out whether there's a vulnerability that you might need to detect.
Okay, but what I was also getting at is that even when you want precision with any kind of realistic language, you have all these issues like reflection and whatnot, and in the end you have to throw up your hands and admit that this is going to miss stuff and things like that. So in practice, working with customers and so forth, has that been a problem where you say that, well, it does seem to find useful stuff, but there are no guarantees here, you still might miss important vulnerabilities?
I find it useful to be honest that we might miss things. Not saying like, expect not to find anything because this tool is useless, but it's going to give you precise results and we're confident in its capabilities, but we can't detect everything, especially those those patterns that you described, things like reflection, things like meta programming structures are pretty hard to, to model or to model sensibly out of the box. What I encourage there as my approach is try and collect information about this beforehand. So the fact that it's really flexible and you can write this customization usually means that if you know what those patterns look like, you know what a previous vulnerability looks like. This is why variance analysis is useful, because you've got one vulnerability that you're looking at. That gets you a long way to knowing how to write some custom modeling that will handle whatever patterns are present in your code base. So when dealing with customers or maybe a new open source project that's using a certain framework, we might look and see, do we model the framework that's being used? Do we recognize the standard patterns there? Do we recognize some of the meta programming constructs there? If so, okay, then we should throw the analysis at it and it should do its job. If not, maybe we have to do some preparatory work and model those frameworks first before we try and get any meaningful results out of the analysis. And this is very much an area for growth. We're always looking for new frameworks that we should be doing, trying to prioritize which ones are really being used widely in the community. It's a bit in the past, but I think we have a honest and constructive approach to responding to that and adding new things. The beauty of it is it's easier to add new things, right? Adding support for a new framework is not, I have to build a new tool. It is, I have to understand what the code looks like, know what the patterns are, and then write a sensible modeling of it in the same language that I'm familiar with. So that's nice.
Okay. Let me ask you sort of for comments on more perhaps speculative matters. So in developer oriented tooling ecosystem, we see increasing presence of machine learning inspired techniques that look for patterns, and in fact you read about papers that find lots of very interesting patterns of code, and you can in fact find similar code once you find a certain pattern and so forth, and all of this is based on sort of pattern matching technology as opposed to more formal methods oriented technology, and such as the one that you described. And I would like you to comment on, do you see in your future going to this soft side of using machine learning based methods in this kind of code analysis, or at least in GitHub
Those
or
are
Semmle?
yeah, those are great ideas, and we are exploring them. So actually at this link there is a description of a kind of a test program called adaptive threat modeling, where it's built on a lot of both programming language and machine learning research, where you might want do something that is less formal. You might say, can we infer properties of the program? Can we infer places where we might want to expand? This is still exploratory, not committing to anything that we will concretely do or put into this at the moment, but we do have folks who are researching this intersection of data science and programming languages and seeing what sticks. It's conceptually super interesting when you think about, as you said, these are formal methods. Things like CodeQL are very deterministic. It's very much like, I find results and I'm giving you some guarantees that there's something for you to look at here. And making that statistical presents a lot of interesting challenges. How do you present the results? What do you consider good enough to show together with these other precise results? So don't have answers to all those things, but we are exploring that intersection of machine learning with more traditional programming language and deterministic input.
Okay, great. Awesome. All right, let me, I don't know if there is something wrong with the platform itself, because I do not see any question on the Clouder one. Maybe we can shift a little bit about, this discussion was supposed to be not just technical Q&A, but more of ask me anything kind of conversation as well. So let me maybe start a little bit of that conversation. In terms of, can you say more from your personal point of how long have you been with Semmle as a startup, and what motivated you to join a startup as opposed to maybe a more maybe join a larger company just as your own career choices?
Yeah, so I've been with the combined Semmle GitHub situation for about 4 years now. Prior to that, I was an intern at Semmle, so I have spent approximately 5 years working with this technology. And I've been looking at my background, like I went to the University of Oxford, and a place where that was known at that point, Uga Demur, who I'm filling in for, was no longer teaching at the university. He had focused full time on Semmle, but it was still like the name was around. I'd seen mentions of the company and what it was doing. So from that perspective, it was very much like a very smooth, almost nepotism path into working in these areas, but primarily because it was really interesting. It was a nice way to apply these very theoretical ideas that you engage with when doing university work in mathematics and computer science in those spheres. That was being useful. It was being turned into things that worked and that solved real problems for the industry. So that was really fascinating. I think that was the main appeal. And Semmle created a good environment for being able to do that combination of research and then make it work at scale. So it made sense. And as we've seen here, the viability of the technology and the dedication of the people who worked on it meant that we managed to scale up, and that got recognized. And now we're part of a much larger organization where our reach is larger. It's nice in the sense that we can reach more users and we have a platform and we can think about how to deliver a better user experience than we would necessarily as a much smaller company. But those core ideas still stick around in terms of innovating.
Perfect. All right. Well, I think we can probably bring this session to kind of a close. If anyone who is watching online, if they are on the Clouder platform or want to join Zoom, if they have any last questions for our speaker, please chime in now. Otherwise, we will conclude this session soon. All right, I think we do not see any questions. So I think this platform does stay live. Your video, I think, is being recorded and will be available. Possibly people can post some questions later on. If so, we can let you know and you can send in your answers. But otherwise, thank you very much for a wonderful talk and for answering all the questions that I asked for the last 20 minutes. Thank you very much.
No problem. Thank you so much for having me. Happy to answer questions that as they come in later on. And if folks want to reach out to me, my contact information is on my Splash profile.
Perfect. Thank you, Aditya. Bye.
Thank you.